Hello and welcome to a video on geometric sequences. So let's look at an example of a geometric sequence. Remember, a sequence is just a list of numbers. So here is an example of a sequence. And typically the curly brackets are used when we're talking about sequences. And then typically if we're ending with a dot 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 here, that means sort of whatever pattern is established with these numbers, that pattern would continue. Those are sort of typical notational conventions. So the first thing to do when you look at a sequence is to try to think about what is the pattern, if there is one. I mean, maybe the numbers are random, maybe there is no pattern. So here we've got 2, -6, 18, -54. Is there a pattern? Well, it looks like 2 times 3 is 6. So I multiply by 3, I get 6, and 6 times 3 is 18. And 18 times 3 is 54, but then we've also got the signs, the SIGN, positive or negative signs, alternating here. So 2 times 3 is 6, but I want this to be -6, so maybe it's 2 times -3. And then -6 times -3 is positive 18, and positive 18 times -3 is -54. So it looks like the pattern here is to get the next number in the list, you take whatever number you currently have and you multiply by -3. So that makes this sequence geometric. In geometric sequences, that's exactly what a geometric sequence is. To get the next number in the list, you multiply the current number in the list by a constant, in this case the common ratio. So usually we're going to use the letter R to denote what our common ratio is in a geometric sequence, the common ratio being the number that I'm multiplying by to get subsequent numbers in the sequence. So now let's try to write a formula in function notation for the sequence. So here's the explicit formula for a geometric sequence. So a of n, that's just the name of the sequence. We'll just call the sequence a of n. So it's the first number in the list, which would be 2, times the common ratio, which in this case is -3, raised to the n minus 1. So there's an explicit rule for the sequence. An explicit rule meaning that I could pick any number I want for n. So for example, if I picked 4, and I evaluated this formula when n equals 4, that would give me the 4th number in the list. So I could just sort of look at the list to confirm this. 1, 2, 3, 4. The 4th number in the list is -54. And if I evaluated 2 times -3 raised to the quantity 4 minus 1, if I evaluated that on my calculator, I would indeed get -54. So you can think of n, the value that you pick for n, is sort of the spot in the list that you want to go to. And with the explicit formula, I could go anywhere in the list. Like I could say, hey, what if n was 50? And then I could evaluate out my explicit formula with n being 50, and that would give me the 50th number in the list, the 50th number in the sequence. Now, just sort of one thing to keep in mind is that sometimes you'll see explicit formulas written in function notation, like a of n here. That's function notation. We're familiar with that. Sometimes you will see subscript notation used. So just be aware that, like, if you ever see like a sub n, that's just another way to write a of n. So say here it's a subscript 1. That's just another way to write a of 1. Like, so a of 1 and a subscript 1, they both would stand for the first number in the list. A sub n and a of n in function notation, those both stand for like the nth number in the list. So if ever you see function notation, that's what we're used to, but subscript notation is just another way to, it's just a different notation, a different way to annotate sort of the same thing. So a of n here in function notation, that's the same thing as a sub n. So just keep that in mind. Now, one thing that I want to look at is like how we could check out some of these explicit forms on the calculator. So let me just pull up my calculator here real fast. So in my calculator, I can sort of check my explicit form using the calculator because I could check the table and make sure that the table for my explicit form matches up with sort of the given sequence here. So let's check this first explicit form. 2 times negative 3 raised to the quantity n minus 1. Notice on the calculator it's going to be x minus 1 instead of n minus 1 because the variable comes up as x here on the calculator. That's fine. I go into the table. The first number in the sequence is 2. The second number is negative 6. The third number is 18. Then negative 54. It checks out perfectly. Now notice though this is only one particular explicit form. There's different sort of functions here that would produce the same list of numbers. So for example, if I had, say, negative 2/3 times negative 3 raised to the x, and then I checked that out, look, that has the exact same table. Or I could try something like negative 6 times negative 3 raised to the x minus 2. If I check the table, look at that. All of those functions have exactly the same table. So this sort of version of the explicit form, that's just one possible, but there's different sort of versions of the function that produce the exact same table. And I'll sort of leave it to you to think about why these different versions are producing the exact same table. That's something that you're going to want to think about for a little bit. So now, let's talk a little bit about what are recursive formulas. So recursive formulas, they sort of give the rule in terms of if you have any number in the list, what do you do to get the next number in the list? So here's how you sort of represent the sequence recursively. So you want to give the first number in the sequence. So in this case, the first number, a of 1, is 2. That's the first number in the list. And then you want to say, for any number in the list, what would you do with that number to get the next number in the list? Well, you'd multiply by the common ratio. So this notation just it looks a little bit confusing. So a of n, that's any particular number in the list. And a of n minus 1 is the number that comes right before. So let's look at an example here. So what if I wanted the third number in the list? What does the recursive formula tell me to do? Well, it says you're going to take the common ratio and you're going to multiply by, so a of n minus 1, if n is 3, this would be a of 2. So see how this formula reads? It says if I want to know what a of 3 is, I need to take the common ratio, which is negative 3, and multiply that by a of 2, which is the second number in the list. Now that totally works. If I wanted to get that negative 50, or this 18, that's the third number in the list, I would have to take the second number in the list and multiply by negative 3. Now, the recursive formula sort of describes the pattern. The recursive formula describes the pattern as I was describing it in the beginning of the video. Sort of from any number in the list, how do you get the next number? But the thing with recursive formulas is that if I'm just looking at this recursive formula right here, yeah, I know that the first number in the list is 2, and then I could start multiplying by negative 3 to get subsequent numbers in the list. But if I wanted to know, say, the 10th number in the list, well, with the recursive formula, I would have to sort of build up the entire list in order. Like I would have to start with a of 1 being 2, and I'd have to continually multiply by negative 3 until I got up to that 10th number in the list. Whereas with the explicit formula, if I wanted to know a of 10, I could just substitute 10 into n and go right to that number in the list. So there's advantages and disadvantages of both forms. And again, over here, I've just written the recursive formula, but using subscript notation. So instead of saying a of 1, I can say a sub 1. Those mean exactly the same thing. And then a sub n, that means exactly the same thing as a of n. It's the common ratio times a sub n minus 1. a sub n minus 1 is the same thing as a of n minus 1. So that's just a quick crash course in geometric sequences and explicit and recursive formulas, and good luck!